All right, good evening. I'm going to give this a try. We're recording from home right now. And I do want to go ahead and give you the chance to watch this whenever you want to learn about quantum mechanics. The topic of quantum mechanics doesn't really fit into one place in the physical chemistry curriculum. We actually have it as our first course in our BS Physical Chemistry series. And here it's just kind of like its own topic that it sort of fits in. It's going to have a little bit of impact on the surface plasmon resonance, but it's not going to have that much impact on most of the other topics that we talk about. And so, what better time to do it than now? So let's talk a little bit about quantum mechanics, and because we mentioned some of the ways in which waves of sound work, I demonstrated some of those to you today. And so I'd like to mention how those actually fit in with the question of what do atoms look like. Quantum mechanics really sounds impressive if you say it to someone else. Say, I'm watching a lecture on quantum mechanics. Feel free to say that to your parents or whatever. But really, it's a question of how do very small things move. Mechanics is just how things move. Quantum means that we're dealing with things that are so small, their energy levels are actually quantized rather than a continuum of states that we can't tell the difference between. They're like the musical notes that I played in class today with that tube. And so, to answer the question of what do atoms look like, we actually don't want to start about talking about the shapes of particles. The shapes of particles is they are what they are. But we really want to start talking about the shapes of waves, because electrons are both particles and waves at the same time. And to understand what atoms look like, you have to understand what the shape of an electron is. So, this is going to be reasoning with physics, and we're going to be going from a lot of experiments. We won't usually talk about the experiments here, but we are going to be talking about the results of the experiments. And I just want to show you a little bit about some of these experiments are really fascinating. We just don't have time to go into the physics of it, but physics experiments are a really cool breed. For example, did you know that you could do a physics experiment with peeps? You could use a microwave and peeps to determine the speed of light. And all you need is really rather simple equipment, but you need to have the mathematical background to be able to use that simple equipment to find out something really kind of amazing. You can actually figure out what the speed of light is. I mean, I didn't know you could do that with a microwave. And so I want to show you that video right here. Now, one thing about the video, so of course they tell you how they're selling something at the end of that, but that is a really cool demonstration of how you can do that. The key is the equation, and that's why the equations are so important to everything we're doing in this class. So rather than measuring the speed of light, what we want to do is we want to measure the shape of an atom. And so you might remember that the history of an atom has gone various stages of resolution. You know, at first, John Dalton knew that the atom was a solid sphere, and that was his model, and that was a huge advance at the time. And actually it took another 100 years for people to realize what was inside that sphere. J.J. Thomson had the plum pudding model, in which the whole sphere was positive, and then it had little embedded negatives sort of in it, like a plum pudding is what he said. The reason why this is broken down into plus and minus is that the atom itself is neutral, and so you have to have a balance of the plus and minus. How does that work? His was the first stab at that, and then actually we found out a lot about the atom within just 2 decades. We found out that Ernest Rutherford found out that the nucleus was actually very small, and the electrons were therefore moving around the nucleus in empty space. Then Niels Bohr suggested that the electrons move around in little circles, like the planets move around the sun. This actually is if you stop someone and you ask them, how do electrons move around the nucleus? If they remember from science class, they will remember Niels Bohr's model. But Niels Bohr's model is not actually accurate. It's actually was only prevalent for about 13 years until Erwin Schrödinger finally proposed the quantum model, which is still the model that stands today, another 100 years later. The quantum model is where, and you notice that the quantum model doesn't have any of those little electron orbitals if you look over here. It's just sort of a fuzzy cloud of electrons. because Erwin Schrödinger realized that electrons are not like planets, they're not like particles, they're actually like waves. This looks more like a wave, a fuzzy wave, than a discrete electron moving in a discrete orbit around a discrete nucleus. So I just want to remind you that quantum mechanics is about how things move. And when you studied physics, you were actually studying a lot of classical mechanics, which means the kind of stuff that Newton did, Newton's laws and things like that. That describes how normal to very big things work. In fact, it describes how even things as small as a nucleus of an atom work. Classical mechanics is pretty good for describing things way down to that size. How the Earth goes around the sun was one of the things that Newton figured out. And so you talk a lot about those things, springs and you know, even up to black holes and things like that, although black holes are so massive that they actually require a different kind of physics. We're not dealing with that, though. We're going to deal with quantum mechanics. And so we're going to deal with very small things. Now, the question of how does an electron move around a proton, which was really the question on that last slide there, is the electron is so small that it actually acts a bit like a wave. And so to say what is the shape of the atom at the electron level, you have to say what is the shape of a wave. So the fact of the matter is, it's not just electrons that have wave properties to them. Technically, everything has a wave property to it. But you don't see the wave. The wavelength doesn't get measurable or even to the point where it can really affect everything until the mass gets very, very small. Now, when we talk about quantum mechanics, we're going to talk about waves, and then there's going to be a lot of stuff that I don't have the time or ability to fully explain right here. You have to understand it in terms of its own logic. And in fact, they've done a lot of the experiments about the question of, is an electron a particle or is it a wave? And the answer is, it's both. It depends on how you look at it. Can you determine exactly where a particle is? Well, you never actually can, because you can't know both the momentum and the position of a particle at the same time. These things don't make sense because they don't cohere with our usual classical scale of things. They don't, cars and cats and things like that, they don't act like this. Only electrons are you getting to the point where you're small enough where the wave-like ability of everything starts to show up and starts to affect things. So, for example, there's actually a theological analog to this. Sometimes you can talk about theology and you get to the point of a paradox, where your language itself doesn't seem to really capture what's going on. I think you get to the same point when you get to quantum mechanics. It's just that you're dealing not so much with words about God, but you're dealing with math about electrons. And yet you still have to reach these points where you have these apparent paradoxes. And you have to follow the logic of quantum mechanics just like you have to follow the logic of the Trinity. The 3-in-1 logic of the Trinity doesn't really work with classical being, classical ontology and things like that, classical philosophy. But you have to realize that God's not on the same level that we are, and so you have to ask God what God's logic is in some cases. So there's an example right here from Alistair McGrath, who actually was a scientist and then he became a theologian. He says the key question when you're talking about the doctrine of the Trinity, he's talking in a theology book about theology here, but notice how he brings in quantum mechanics. The key question is not, is this reasonable? That question is actually a flawed question. It presupposes that the rationality of faith may be mapped onto a common sense rationality, whereas the real task of any responsible Christian theology is to discover the internal logic of the Christian faith, not to lay down in advance what form this should take. Quantum mechanics and Christian theology alike are perfectly rational enterprises. The difficulty is that their logic seems counterintuitive if they are judged by the socially constructed notion of common sense. It's the common sense that's the issue when you're dealing with something that's very distant from your own experience. God is very distant in one direction, electrons are very distant in another direction. And in fact, it's kind of funny. If you look at quantum mechanics, there was a talk that I went to at a conference once that made this point. He said, pull up the Wikipedia on the interpretations of quantum mechanics. The math of quantum mechanics has a very consistent logic, and it's been proved to like 17 decimal places. The math of what I'm telling you is very established. But what it means is something that everyone is still arguing about. And so the person who was doing this talk pulled up this plot that you can see from Wikipedia. How many interpretations are there of quantum mechanics? Well, there's at least like 13 or 14 right here. And they all have their own flavor of certain answers to certain questions. What is real? What is hidden? What can be seen? How does the wave function collapse and all that? And to really get into this, you have to really get into the whole physics version of this class, which in one lecture we don't really have time to do. But the thing about this is that it's kind of like if you pull up the Wikipedia page on Christianity, you'll see all these different denominations, I should say, that have different answers to very fundamental questions. And there's almost the exact same thing going on when you have these different interpretations of quantum mechanics. It's almost like there's an analogy here. So I want to say that there's what it all means is definitely up for debate, and it's one of the most fun things to talk about, in my opinion. Mind-blowing in many different ways. And you can get into what each of these people say about what the interpretation of quantum mechanics can be. What I'm going to talk about is what it is. And the whole thing is, there's no question about the shape of the atom. The question is, what does it mean that it depends on how we look at it, whether an electron is a particle or a wave? What does that really mean? It can't be both, can it? But the experiment says it is. So I'm going to give you the experimental results, and then in seminars someday and out of class, we can argue about what it means. Okay, so the crucial weird insight that we're dealing with quantum mechanics is that everything, and especially electrons, is both a particle and a wave at the same time. If you ask the question, is this a particle or is it a wave? The answer to that question is yes. So a bunch of waves can also be seen as a stream of particles. So photons are waves. They hit electrons, which you think of as particles, but they actually have wave-like functions. And the two waves, the photons and the electrons, can interact like waves interact. Remember that photons can hit electrons, they can give them energy, they can push them to a higher energy level. And those energy levels are actually one of the main topics that we talk about in physical chemistry. So a bunch of waves can be seen as a stream of particles. If you're thinking of a photon hitting an electron, that hitting even has an idea of a particle nature to it. But they're actually both waves as well. So the other flip side of this, every particle is also a wave. Again, this is true for everything, no matter how big, but it's really only noticeable or non-negligible for large or very small things like the electron. The equation for this is that the wavelength of the wave of whatever the object is that you're talking about, its wavelength is inversely proportional to the momentum, which is mass times velocity. So that's what we have this, from that we can write this equation. The wavelength lambda equals some constant divided by mv. So something very big with a lot of mass is divided by a very big number, and so you end up with a very short wavelength, something that's so short that we could never even hope to measure it. But something very small would have a much larger wavelength. And it turns out that electrons have wavelengths that are large on the scale of an atom. So I'm going to return to this picture a lot of times. In the beginning, what happened? We have this timeline of history, and the whole thing is, in the beginning there was a big bang, and then a lot of stuff happened, and the World from Dust book is about that story. So 13.7 billion years happened, but let's look back to the very beginning. It's really interesting. Look at this. This is, I believe this is Carl Sagan's. It's the work of him or someone like him. And you see what the very first thing is. You have quantum fluctuations, inflation, and then light. In the beginning, there was light. The afterglow light pattern happened at the very beginning of this graph. I think that's a nice juxtaposition. And the light condensed into matter. We're not going to talk about that because we're dealing with the matter universe in physical chemistry. The light, or the energy, separated into heavy positively charged protons, heavy neutral charged neutrons, and very light negatively charged electrons. Overall, there was an overall neutral charge, but the thing is, the plus charges were very heavy and the minus charges were very light. And this difference caused the atoms to form the way that they did. All the protons are basically the same mass. They're all much heavier than all the very light electrons. So the same charge in very different masses results in the nucleus positively charged and the model of Schrodinger's model of the electrons moving around the nucleus. The protons, the pluses, would attract and constrain the electrons, and so the electrons, you know, they could fly around a little, but they would be pretty much tied to the proton to make a neutral atom. That would be roughly spherical shaped. So again, John Dalton, to the resolution that he had, was right. Electrons are so light in terms of mass that they can be described as waves of light. Now remember that one of the quantum things is that you can't measure both electron position and momentum at the same time. Because you can't measure both the position and the momentum, you can never know both of those things at the same time. And so if the particle is moving at all, if it has a momentum, that means you can never know its exact position. This is the uncertainty principle. Because of that, the particle is spread through space like a wave. A wave is spread out through space. It has a wavelength. And a particle, like an electron, will also have a wavelength. So we can calculate this. If we do the math for waves, we can calculate where the electron will be. An electron that's being pulled on by the positive charge of the nucleus, the proton, we can find that's going to be very high in energy over here and low in energy over there. In fact, if you have the positively charged nucleus and you have the electron moving around, we can calculate where it's going to be most stable. Guess where it's going to be most stable? It's going to have the lowest energy and be the most stable right on top of the plus. The minus is going to be most happy right on top of the plus because the minus and the plus are pulling on each other. So we can do that, and we can actually see, I'm going to show you, the math brings you to that point. Now, the position of the most stable positions of the electron, the relationship of position of electron to energy of electron, is actually the square of a mathematical thing called the wave function. So you have the wave function, you take its square, and that will tell you where the particle is most energetically stable. That will tell you the shape of the atom, the position of the electron. But remember that it will never be an exact position. It's going to only be a probable position. You'll have a 90% chance of finding the electron in this space, but there's a 10% chance it'll be out here. So, the thing is, waves are, most of what you've been taught, at least what I was taught up to this point, was one-dimensional waves. When we're talking about electrons being constrained by a nucleus, that's actually a three-dimensional wave. And that's going to be really, you know, a cube as complex as the one-dimensional wave. So we'll start by talking about the one-dimensional waves that we're used to, and then I'll show you where all the math happens, and then I'll show you what the result of all that weird math is, okay? So, what is a wave function in one dimension? Well, they give it the symbol psi, and here's an example actually from your book. You don't have to read this chapter, but it's there in your physical chemistry book. It's just chapter 9. So they call it psi, and so the position of the electron will be gotten by taking psi squared. Psi squared is the probability of finding a particle, the electron, at a particular point in space. And so it's actually a function we can do a little calculus. The probability of finding a particle in a volume dV is proportional to psi squared dV. And if you actually just solve that, you actually have the expression for where the electron is. What is the shape of the atom? Okay. So this shows you over here, this figure 910, shows you the psi is sort of, you see you have a wave going up and going down for psi. Then you take psi, but you take the square of that, and the negative part becomes positive. The shape changes a little bit too, but mostly what happens is everything becomes positive, and it shows you that the wave up and down becomes a wave with two peaks. And it has, in the middle, it has a place where the probability is always 0. You will never find the electron at this particular point right here, because the probability of finding it, the psi squared, is 0. That's called a node. And so the high points are where you're expecting to find the electron on psi squared. The 0 point is a node where you won't have any electron at all. So I can show you what these waves look like. Now the thing is, waves only make sense when they are tied down at both ends. When you have a standing wave, you have a wave that's tied down at both ends, and you can actually see the wavelength of it. You can see it going up and down. Now, the one thing I forgot to bring today was I forgot to bring my 3D standing wave machine. So maybe I'll take that to class one of these days, and I'll show you what it is. But all it really is it's taking a one-dimensional string, and it's lighting it up with these cool lights, and then it rotates it at different rates. And depending on how fast you rotate it, you get different numbers of nodes. The important thing here is if you put more energy into it, you rotate it faster, you get more nodes in your standing wave. Like right here, you see that this example has 2 nodes in the wave, whereas the last example back here has just 1 node in the wave. More energy means more movement of the electron. More movement means more nodes. And it actually means fewer places where the electron can be, because we have these 2 nodes now where it can't be rather than 1. So the thing is, standing waves have to be constrained. The thing about standing waves is they have to be tied down at each end. Remember that we had that example of the instrument that is the thing about a simple situation, a simple wave, is that it has to be tied down at the end of the box. And so the classic way of talking about a simple one-dimensional sort of electron is you say you have a particle in a box. What is the energy of the particle in a box? Remember, it's not just a particle, it's also a wave. So this particle has to be tied down at each end. Its wavelength has to be tied down at each end. And so you have the length in one dimension. You have the particle constrained to be in a length of 0 to L, you know, the box of size L. And you just make it a simple situation where the electron is very stable, very low energy. Inside the box, V energy equals 0. They're using V, by the way, because this is technically potential energy rather than E energy, okay? And outside the box, the energy is infinity. And so the electron can only be between 0 and L. And so because the wave has to fit in the box, has to be tied down at each end, there's only a few ways to do that. For being tied down at each end, for example, you can have it tied down at each end, and you can just have this blue line down here at the bottom. Then you can have it tied down at each end, and you can put a little more energy into it. You see the energy scale has gone up here. And you end up with 1 node in the middle. And you end up with 2 parts to the wave. You can have 2 nodes, 3 parts to the wave, if you add a little more energy. And a little more energy, you have 3 nodes, 4 parts to the wave. As you go up in energy, you will get these different, and you can imagine putting more and more energy in and getting more and more nodes. But the whole thing about this, notice that all of these energy levels, they're tied down at the ends. You don't have n equals 3.5. You don't have, you can't have half a node either. So the way that the wave function works, a particle in a box is going to only be able to adopt these particular levels. So the particle in a box, its energy is quantized. It can never have, less than this half a wave right here. It can never be anything other than that, because the wave has to be tied down at each end. And that means that the energy can never be between these levels. It only can be at these levels. So this is actually the exact same thing. This is like a piano strings. So like any musical instrument, strings that vibrate, the strings are tied down at each end, and they can only vibrate certain ways because there's some factors with like the tension of the string and things like that. But the important thing is the length of the string is one of the main determinants of how the string will sound. Just like the length of the box will determine what the energies are that the particle can adopt. And remember, when I say particle, it's also a wave. So notice how you have more nodes. Each node is where it crosses this sort of zero line for the energy. And you get more nodes when you add more energy. But you don't have any halfway energies. So I showed you that thing in class, the tube, and realized that the tube was actually just a flexible pipe. In a sense, I said it was like a flute, but it's even more like a pipe organ. And a pipe organ just has a bunch of tubes like what I had, and each tube makes its own note, right? But you move the air through, and it makes, depending on the length of the tube and the thickness of the tube, but that's 2 dimensions, so let's just think about 1 dimension. Depending on the length of the tube, it will make a different note. So I can only ever get 5 notes out of the spinning tube that I did. And those are called the overtone series, and those are actually equivalent to these simple waves that you can make by plucking a piano string or by putting an electron in a 1-dimensional box. More energy in means a higher note out, means more nodes. So the thing is, for a particle in a box, 1 dimension has to be tied down at the ends. What if that 1 dimension is in a circle? Instead of being tied down at the ends meet right in the middle of the circle. And that means that the ends have to match. And so you still have a quantized situation, but it is a quantized situation where the line you're dealing with is a circle. And there's actually a figure in chapter 3 that shows this in A World from Dust. So look for that figure. And it's one of the reasons why, how you can start to imagine more dimensions than just a 1-dimensional particle in a box. What if it's a circular type thing? It's the same deal. The waves are still quantized, and there's still only so many ways that the waves can wrap around that circle. So we want to ask the question, where is the electron in the hydrogen atom? And so we're going to pull out our physics equation right here, okay? What I'm going to show you is, this is where we start to get to the math, where we don't necessarily have to follow everything that's going on. But what this really is this is actually not that bad of an equation at the first level. It gets a little hairy when you get into it. But the main thing is that this equation just says the kinetic energy plus the potential energy equals the total energy. The kinetic energy for a wave, you take the psi and you do all this weird math to it, and you add the potential energy, which is the V times psi, and that equals the total energy, which is E times psi. Now this is all some really math that's honestly, I've forgotten how to do a lot of this. I'd have to really brush up on it. And so I'm not going to say what all this math means, except to point out one thing. Notice something about this. This is the psi, which is the location of the particle, in x, which is the x displacement of the particle. There's actually, if you look at this really carefully, you can kind of imagine that it's you can sort of see an mv squared in it. Look at, there's the m, which is the mass of the particle. And this is a change in position squared. This is like the m part of 1/2 mv squared. And this is like the v part, because the v part is a d over dx. If you had that part of physics in terms of calculus, that's how you express a velocity. It's a d over dx. And so it's kind of cool that you can actually see the mv squared. The reason why this is squared is because velocity is squared. And this is actually just 1 mv squared for a very small wave of a particle, instead of actually being like something you can measure in physics class, okay? Same idea, different math, okay? So the important thing is that you see the second derivative And you see that that actually there's a sort of 1/2 mv squared hidden inside of it. So we've got to simplify this thing. And actually it's a big challenge. It's one of the things that Schrodinger helped people figure out, is how to simplify this thing. So the way to simplify things in physics is that you introduce boundary conditions. You introduce things that you rule out the impossible thing so that you're left with the possible. Sort of the Sherlock Holmes way of doing things. He once said that. And so the boundary conditions are you define what's possible and what's impossible. So one boundary condition is that positive charges on the proton will attract negative charges on electrons. Plus and minus attract. The plus is holding the electron within a certain boundary, and that's a boundary condition. So all of these are things that you actually already know. You just are putting them into the math this way. Another thing is that the three-dimensional wave has to fit in the three-dimensional box, which is the energy well caused by the proton. So the proton is attracting the electron, and the electron is a wave. It has to fit into the box that the proton is making for it. The proton is providing boundaries, and this is where the 3D thinking gets a little bit weird. But the important thing is, in a sense, the three-dimensional box is defined by the proton. The proton's holding on to the wave of the electron, and it has to fit. The wave has to fit into the box. The ends of the wave have to meet or tie together. Just like having the circular wave, the ends of it have to meet because you can't have a halfway wave, or in the one-dimensional situation, the ends have to be tied down. So it's really all just the equations for what if I have something that has this amount of positive charge on it and has this mass, and something that has this amount of negative charge on it, which is attracted to the positive charge, but it has a very small mass. And the very light particle will act like a wave. So how do you envision multidimensional waves? Well, I want to show you some experiments in this case. This is a Rubens tube, which is a way of visualizing waves through gas burners and things like that. But you can imagine, actually, there's a 1D Rubens tube. You can look that up, and you can try to see what that looks like. That just looks like a wave of flames going up and down. Here's that same thing, but in 2 dimensions rather than 1. And so I want to show you what this looks like. And again, I hope the audio is okay. Just beware the audio might freak us out for a second here. And of course we have to have the ad that we can skip through.
Just press play, Lee?
All right.
Yeah, go for it. Whoa!
Now you may have seen a Rubens tube before. That's basically a pipe with a bunch of holes in it, and you pump in a flammable gas and light it on fire. So you basically create a row of Bunsen burners. What's really cool is to play some sounds into the tube, and you can actually set up standing waves. That is, there are areas, there are patterns of the vibration of the air where there's a lot of vibration in some parts and not very much vibration in other parts. Now that affects the flow rate of the gas inside that tube into the atmosphere, and so it affects the height of those flames. So basically you can visualize the standing wave pattern.
All right, you can go back and you can watch the rest of that video later if you want. I'm going to turn this off because I've been burned by YouTube's autoplay before. Okay? But the thing I wanted you to see is at the very beginning of the video, you see these complex patterns that result in 2 dimensions. That is the result of the sound waves interacting with the different burners that they have right there. And you can see that it's constrained by the square of the 2-dimensional table. And it results in some really interesting patterns. There's nodes and, like he mentioned, antinodes, places where the flames are and places where the flames aren't. And so there are some really amazing patterns you can get from this. If you have a cup of water and you set up your camera right to take pictures of the ripples in the cup of water, and then you play different piano notes. Like here's A, if you play A, then it will make this shape in the water that you can capture with your camera. The cup itself constrains the water in 2 dimensions, and then the sound waves provide the vibrations to the water, and they make these amazing patterns. Like right here is A, there's D sharp, there's E, and you can see as you move through the piano. Actually, I have my family's piano right here. I could go play it, but I don't even know enough about that to be sure I'm playing the right notes here. So I'll let this picture do it for myself, and I'll trust that this person did it right. But it's amazing what these 2-dimensional patterns are that happen when you have a sound wave interacting with a medium that can be a wave, like water in this case, or if an electron can be a wave, you can have a similar shape that results. And so you can actually use this in chemistry. There's a group of chemists that have gone through, and one of the problems in chemistry, how do you put these very little things into the precise place where you want them to go? Because you can't really use your hands in chemistry with atomic force microscopy excluded. You aren't picking up atoms and moving them around. But if you can do these 2D wave patterns, and if they can move flames around, maybe they can move chemical particles around, and they can make reactions happen in the same sort of complex shapes. So that is exactly what this group did. They had a liquid template, they played sounds through it that resulted in 2D patterns, nodes and antinodes, and that moved the little particles around to make different shapes. And then the particles, they froze the particles in place, and they made different assemblies that were very small by using the sound to direct where the particles would go. This is their idea right here. So you have sort of the floating, and the important thing is this is on a cup of water. This is like that piano thing that we just showed you. And they play different structures, like they play something that makes this round structure, and all the particles go into the round structure, and then you react them, and they form the round shape that they have. Or you play a different sound, and you can make assembled structure B. Depending on the sound you're doing, the standing waves, see right here, standing 2-dimensional waves, will shape where the particles will go. And here's some actual examples of that. Here's the shape of the sound on the bottom, and on the top, part C, you see where the particles go, and you see that the sound is shaping where the particles go. If you change the shape of the waves, it will change the shape of the particles. And I just think that's really cool. If you change the shape of the cup that's holding it, you'll also change the pattern, and you'll get a new structure. So here's an example where they have different shaped cups holding the liquid. And you see that you have these different shaped cups. They result in very different shapes on the inside because the waves are interacting with the constraints that they have. The waves are held in place by the box. But you can make these shapes very reliably by following this technique. And so the very last thing is this has led to some really cool art. This is an artist called Berenice Abbott. And what she did is that she made wave pattern photographs by dropping pebbles into water. The pebbles created vibrations, and right here you can see 2 pebbles were dropped side by side, and you have waves that are constructively and destructively interfering. It makes for a very beautiful pattern. She put a glass plate in and made a different pattern, and you can see these cool kind of waves showing up. This is my favorite. I just like the way it has the angle, and you can see sort of the way the corner is moving around right here. And you can see sort of this crossed pattern right there. And it's just a really cool kind of idea to let the waves make the art for you. So you can let the waves make particular shapes. This is what it does in 2 dimensions. And so the next question is, what does it do in 3 dimensions with an electron? That's going to be part 2, and I will record that next.